to this computer. Okay, now we are here. It is March 17, 2025. Right now it's 10 a.m. Pacific time. What did I say? I said that exam number 1 is going to be the day after tomorrow from 9:40 to 11:40 on Canvas. And I'm excluding lab number 1 for exam number 1. Okay, let's leave lab number 1 for the second exam. And the material that's going to show up in the first exam is this one that you see right in here, chapters 18 and 19. Some of the sections of chapter 19 has been excluded from the first exam. Okay, what we have covered so far, which is going to be material for the second exam, is going to be labs 1 and 2. And so far we have those sections of chapter 20. Okay. Some of those sections we are going to skip, like this one. Others we are going to, this one too, we're going to skip. We're not going to cover that. Others we're going to leave for later on, alternate current. And I want to cover electric power maybe today, okay? Let's see if we have time. Okay, measurements of current and voltage is whatever we have been doing in the lab. So I'm not going to cover here, check the lab. Check the lab. And we'll be able to cover capacitors in series and parallel. Okay, RC circuits too, we're going to cover. Okay, and like I mentioned before, to find equivalent resistance in a circuit, you must identify whether the resistors are either in parallel or series, right? And there might be conditions, situations in which you cannot identify connections in series and parallel, okay? For these types of circuit, that you cannot recognize, for this type of circuit, where the resistors are not connected in series, you must use a different technique called the Kirchhoff rule, okay, which is far more powerful, which is Kirchhoff loop law. Let's put it loop law. Let's see how your book call it. I like to call loop law. Sometimes book change it. You go Kirchhoff rules. That's how he call it. Yeah, Kirchhoff rules. It's also considered a law. Okay. So Kirchhoff rules apply not just to those fancy connections, but it also applies to resistors in series and parallel as well. So it's far more powerful law. And, Kirchhoff's rule, let's say, or Kirchhoff's loop law, which is far more powerful than any other technique that requires the identification of connections in parallel and series. But Kirchhoff loop law goes even further, goes much further than that. Kirchhoff loop law allows you to solve this type of circuit here that you see right in here. You see here, we have 2 batteries in this circuit. Okay, we cannot apply Ohm's law in a straightforward way for this type of circuit. You add 1 battery in there, you won't be able to solve the problem using resistors in series and parallel. Okay, and which other type of problem? Okay, here you go, another type of problem. 2 batteries again, right? And there are others too. Instead of resistors, there are also circuits that involve capacitors as well. Okay. Okay, if you can have capacitors connected in series or in parallel. Here's an example of capacitors in series. In order to solve this type of problem, you have to use Kirchhoff's loop law as well. Okay? So that's how genetic the Kirchhoff loop law is all about. Okay? And so let's see how we can use Kirchhoff's loop law. This problem that you see right here is very difficult to solve. It's very mathematically intensive. Okay, it's very mathematically intensive. So what we're going to do, you're going to start with simpler problems. Okay, it is possible to solve this problem using Kirchhoff loop laws, but it's lots of work. Okay, it's going to be 1, 2, 3, 4 equations. Okay, it's going to be a total of let me see, maybe even more. 1, 2, 5 equations now. 3, 4, and 5 equations. Okay, it's going to be a total of 5 equations. And as the number of equations in your system increases, it becomes more and more difficult to solve mathematically. Okay, that's why I'm going to do something simpler. I'm going to do something like that here, so you can understand how Kirchhoff's loop law works. Okay, so let's write down right here. Okay. Kirchhoff's rules requires the recognition of loops and or junctions in a circuit. Okay. In this case here, the simplest one that you are seeing, we have only one loop. We do not have any junctions whatsoever in the circuit. And I'm going to give you an example of circuit with junctions later on. Okay, and the loop that we are talking about, the single loop, is this one right in here. Okay, so here you go. I'm going to draw the loop. See, I call it the loop number 1. Loop the loop. Yeah, let me move it a little bit up. You know what? I'm going to do better. I'm going to give the illusion, right, that we are playing a movie here. Okay, here you go. First circuit, and then we put a loop in there. Recognize, we mark that we have a loop in there. There's no junction in there. Because of that, this is a very simple circuit. Okay. Okay, so the first thing you have to do, you have, let's see, just like I said, let's go back here to my notes, right? Kirchhoff rule requires the recognition of loops and junctions in a circuit. In our first example, we have only one loop and zero junctions. Okay. So what you have to do? Choose an arbitrary direction for your loop, just like I did, and name it loop number 1. Give it a name. Okay. And I will copy this guy here into my notes. Move it. Okay, click there. And then after labeling your loop, notice that I put the loop in the clockwise direction, but I could have had also put the loop in the counterclockwise direction and still solve the problem with the same result, with the same final result, okay? So in this problem here, we know V1, V2, R1, and R2, okay? In this problem, the parameters V1, V2, R1, and R2 are known. Okay, we want to find the current flowing through this circuit. R1 and R2. The current flowing through the circuit. Okay. And I'm going to reorganize it. Okay, I'll leave this way. What's the next step? You know, first step, in our first example. Okay, let me reorganize it better. In our first example, the parameters V1, V2, R1, and R2 are known. We want to find the current flowing through the circuit. Okay, in this example, we have only one loop and zero junctions. Choose an arbitrary direction for your loop and name it loop number 1, just like I did. And now once you see this naming, you can start solving the problem. Now you may start solving this problem. Okay? And the way we do it is like that. First, label the current, the direction of the current. You can put your current in whatever direction you want. Okay? In this case, I'm making the current flow in the same direction as the loop. Okay? Next, label the direction of your current. In this case, I decided to put the current in the same direction as the loop, in the clockwise direction. So I'm going to copy this one as well and paste there in my notes. Go. And now the real mathematics starts. Now the real math starts. Okay? Solving the problem consists in walking through the circuit element by element. Okay, and you can start wherever you want. Okay, let's say we're going to start right here at this point to the left of V1. Okay, you can start anywhere you want, but let's, for the sake of solving this problem, let's start at point A. Here you go. I'm marking point A, B, C, and D. Okay. Copy this one as well. That's where the real mass of the problem starts. Okay. First, label points along your circuit to help you solve the problem, okay? Note that I didn't put a point C here. I didn't put a point C here. Why is that? Because I do not have any elements here whatsoever. Only a regular wire that has no resistance whatsoever. Let's assume that we have no resistance whatsoever, okay? That's why I didn't put a point C here. Because a regular wire is not considered an element, has not considered an element because it has no resistance. Okay, so here you go. We are going from point A to point B. What happens? We are going to a region of negative electric potential to another region of positive electric potential. We are increasing in electric potential. That's what it means. Okay, so going from points A to B, we go moving, right? Instead of going, moving. We go from a region of lower potential, the negative, right? Negative, to a region of higher potential, positive. Consequently, we may write the first term of our circuit. Here you go. The real math now starts. Let me go. Here you go. I need something like that. The first term of my equation is going to be what? It's going to be plus V1. Okay? That's what the first term going from A to B. Moving from A to B. Okay? And then when we go from B to C, we go through a resistor. Okay? We go through a resistor. If we move through a resistor in the uphill direction, not uphill, but downhill direction, in the direction of the current, if we move across the resistor in the direction of the current, we lose electric potential. Okay? We lose electric potential. So it's going to be something like the following. Okay, moving from B to A, comma, we cross resistor R1. We cross resistor R1. And lose energy because we are moving in the direction of the current. So we can here write our equation the following. Here you go. From A to B, we are going to add another term here. From A to B is going to be plus V1. From B to C is going to be minus V of R1. Okay? Like that. We have a negative sign here because we are moving across the resistor in the direction of the current. When we move in through the resistor in the direction of the current, we lose electric potential. The resistor is an element that spends energy. Okay, the resistor is an element that spends energy. And now moving from not B to C, right? We go B to C. Moving from C to D, what happens? If we move from C to D, we are going to cross another battery. But note, see that we are going from a region of higher electric potential to a region of lower electric potential. For this reason, we lose potential energy. Okay? And I can, C to D, we cross a second battery of voltage V2. Voltage V2. Okay? Because we are moving from a region of higher to lower potential, we lose potential energy. And our equation should change and we lose potential energy. Okay, lose potential energy. So here you go. Now my third term is going to be minus V2, okay? And then we have finally our last term, moving from D to A. Moving from D to A is going to be similar than moving from B to C, okay? Moving from D, we're closing the circle now. Moving from D to A, we are going to cross a second resistor in the direction of the current. And we are going to lose electric potential again. Okay, moving from D to A, we cross resistor R2 and lose energy too. And lose energy again. Because we're moving the direction of the current. And so we have that, this other term is going to be just like this term, but instead of R1, we are going to have R2. Okay. So we came to the beginning, right? We start at A, we ended at the A, and then what do we do next? We finish our equation by writing equal to 0. Okay? That's how Kirchhoff rules work for this type of simpler circuit. And later on, we're going to do other types of circuits that are a little bit more complicated, a little bit more difficult. And then we can start solving the problem, right? Remember, we want to find the current I. Okay? We can do that by applying Ohm's law. Ohm's law through each of the resistors that we have there. V1 is already a number there. We know. Here we should not know. All we know, we don't have a number yet. And here we do not have a number yet. But we can use Ohm's law. That's going to be I R1. Okay? And here is going to be I R2. Okay? The negative here means that we are losing potential energy. We want to find out the current. Okay, that's what we want to do. We can finish this job here. Here you go. I'm going to put the I next to each other, right? I'm going to put I in evidence here. And when we put that in evidence, we have to change the sign. We want to solve for I because we know everything else. What I have to do, I have to pass this term to the right. When we pass to the right, we change the signal. And then we finally solve the problem for I. That's the final solution of our problem. V1 minus V2 divided by R1 plus R2. The two, notice that the two power supplies, they are subtracting from each other, right? They're subtracting from each other because they are pointing against each other. See that? The positive of this power supply is facing the positive of the other power supply. If you want to boost the current, you have to change the direction of this power supply here. You gotta put the positive on this side and the negative on this side, okay? So that's our first example on Kirchhoff's loop law. Let's see, let's take a look at this one, this other example, okay? Now, not only we have loops, but we have also a junction. And I'm going to erase those currents for now, okay? Like I said, you know V1, V2, you know R1, R2, R3. Find all the currents in the circuit using Kirchhoff loop law. Oh, one more example. Yeah. Another example. We go. Now, in this example, in this second example, the parameters V1, V2, R1, R2, and R3 are known. R1, R2, and R3 are known through each branch of the circuit. Okay? Just like before, we must identify the loops. Okay? Here, I'm identifying just, yeah, okay, here. Let's start with the loops, right? The loops is easier to identify. Here you go. Identify the loops. In this case, we have three loops, 1, 2, and 3. Okay? 1, 2, and 3. And then identify the junctions. We have one junction here, another junction here. Okay? So I'm going to mark the junctions. Junction 1 and junction 2. And I'm going to, here you go. let's see. I want to do it in a different way. Let's do it a different way. Here you go. Let's identify the loops. Let's do it this way. It's better. Okay. Identify the loops. And then we can write it down here. Identify the loops. Okay, and next, identify the junctions. And I already identified the junctions for you, right? So let's start with the identification of the junctions and loops. And then we worry about the rest. Identify the junctions. And I'll call that junction 1, J1. J for junction, right? And junction 2. Okay, so going back, that's my notes. In the second example, the parameter V1, V2, R1, R2, and R3 are known. We want to find the current flows through each branch of the circuit. Okay, so I'm gonna, we already have that here, right? Solution. Solution. Identify the junctions. Identify the loops. All possible loops that you have in there. Identify the junctions. Identify the junctions. That's the next slide. J1 and J2. J1 and J2. Okay. Next, now we're going to do label the current. Label the currents in the circuit. Okay, so here you go. I'm calling this one I1 because it goes through the resistor R1. Okay, and we have power supply V1 too. Okay, I'm calling this one I2 because it's coming from the battery V2 and the resistor V2. And I'm calling this one I3 because it goes through the resistor R3. Okay, notice that we have a junction here, right? Let me go back here and put the junction there. Like this one. Like this one. Okay. And what else can we do? Okay, we can label the current on the other side as well. Notice that there is no junction between this point and this point, right? So the current flowing through this resistor is still going to be I3. All I have to do is to change its direction. Okay? And it's the same thing for I1, okay? I don't have to change the direction because this guy didn't, write like that, okay? I1 flows to R2. And the I2 can also be displayed right in here, but with a contrary direction. Positive direction. Okay? Because this flow here must be coincident with this flow here. The flow of this current must be coincident with the flow of this current. Okay? Now there is a little secret about the loop law. Okay? Label the currents in the circuit. Okay, so let me put the current now. I'm going to copy the current as well. See how this drawing is becoming. We are adding more and more information to this drawing. Okay, so here we go. Get it? And paste there. And like I said, the direction of the current can be whatever direction you want. Okay, it doesn't have to be from the left to the right. It doesn't have to be up, down, okay? It can be whatever direction you want, but make sure you follow through is the same direction throughout the solution of the problem, okay? And now there's a little secret that you should know about the Kirchhoff's loop law. A little secret about Kirchhoff's loop law. Kirchhoff's loop law. Each loop and each junction provides you with a mathematical equation that can be used to solve your problem. Okay? Let's say, however, okay, so suppose, however, you will need only each loop in junction provides you with a mathematical equation that can be used to solve your problem. Assume that we have m loops and n junctions. In this case, m is equal to 3 and n equal to what? 2, right? M loops and n junctions. A little secret. 1. Each loop and junction provides you with a mathematical equation that can be used to solve this problem. Okay? 2. Assume that we have 3 loops and 2 junctions. Okay? And the secret is this one that I'm going to tell you right now. You need only m minus 1 loops and n minus 1 junctions. Solve this problem. Okay? So m minus 1, okay, m minus 1 is going to be equal to 2 equations, right? And n minus 1 is going to be equal to a third equation, to one more equation. Okay? To solve this problem, you will need to solve a system of 3 equations, right? 2 equations related to the loop and 1 equation related to the junction. Okay? And we are going to do that. Let's take attendance first, and then let's go to our break. It's almost 10:45. I'm going to take attendance, and after the break, we solve this problem. Today is the 17th. Remember, it's a problem with 3 equations, a system of 3 equations, and 3 unknowns, right? Notice there's 3 equations with 3 unknowns. What are the unknowns? The unknowns are current 1, current 2, and current 3. Because we have 3 equations and 3 unknowns, in principle, you should be able to solve this problem mathematically, okay? Now, let's see. Abir Ahmad, are you there? Hello, Abir. Hello, Abir.
Hi.
Nestor Alvarado.
Here.
Thank you, Nestor. Monte. Monte Ambarshian. I don't see Monte here. Hasti Amin. I don't see Hasti either. Isabella Ballesteros. Isabella. I don't see Isabella either. Justus Bowden. Are you there, Justus? Okay, just must be away from his computer. Alexandra, are you there?
I'm here.
Thank you. Benjamin Carvajal. Thank you, Benjamin. Brianna Carrillo. I don't see Brianna. Elizabeth Castellano.
Here.
Thank you. Natalia Cordoba. Are you there, Natalia? Let's see. Yeah, I don't see Natalia here in my list. Jacqueline Delgadillo.
Here.
Thank you, Jacqueline. Jenny Diaz.
Here.
Thank you. Valerie Diaz.
Here.
Thank you. Juan Escalera. Juan shouldn't be here, right? Bianca Eulaki.
I'm here.
Dana Gomez.
Here.
Thank you. Edwin Gonzalez. See. Okay, Justice just replied. Okay, what about Edwin? Hi, Edwin. Okay, I'm gonna put a star here on Edwin. Ellie Gonzalez.
Here.
Thank you. Next is Manuel Hernandez.
I'm here, Professor.
Thank you. Samantha Huart. Hello, Samantha. I don't see Samantha here. CJ. Hello, CJ. I cannot hear you. Just type there in the chat window, please. Looks like your mic is turned off or it's not working. Okay, CJ. I'll give attendance. You can turn off your mic now, CJ. Luis Leal. I don't see Luis, not here. Amber Lopez. Thank you, Amber. Next is Arely Lopez. Thank you. Genesis Lopez. Hello, Genesis. Okay, I'm gonna put a star here for Genesis. Next is Mary Michaelian. Hello, Mary. Mary must be away from her computer. Next is Ramon Olivares.
Here.
Thank you, Ramon. Next is Taylor.
Here.
Thank you, Jeremy Pittman. I don't see Jeremy here. Okay, next is Stephanie Ramos. I don't see Edwin. Edwin is here, right? Okay, Stephanie, I don't see Stephanie. Leslie Rios.
Here.
Thank you. Jason Strait.
I'm here.
Thank you. And Hema.
I'm here.
Thank you,
Hello,
Hema.
Professor.
Yeah, who is that?
It's Genesis. I'm here.
Genesis, right? Genesis.
Yeah.
Locke? Okay. What about Mary? Mary, are you there? Okay, thank you. Let's see. There's one more student here. Edwin, right? Edwin. Yeah. Okay, thank you, Edwin. Let's see how many students we got here. 24. Yeah, it seems that there is one more student here that didn't answer. Who was that? Galia. Oh yeah, I gotta put your name here. Thank you, Galia. Galia Odabashan. Odabashan. Anybody else was not called? And we go. One more issue. Now we have 25. Good. Now we have the right number. Let's 10:49. Good. So let's go for our break. Break 11 a.m. to 11:15 a.m. And I'm going to stop sharing the screen. Pause my recording, and share. We go. Now let's start solving our equations, right? So let's start with loop number 1. Remember, I need only 2 loops, right? And you can choose whatever loop do you want. You still get the same. You still get the same answer, no matter if you choose loop 1 and 2. You get the same answer if you choose loop 1 and 3, or loop 2 and 3. You still get the same answer, final answer. That's the neat thing about this technique. It is mathematically consistent. Okay, and loop 1. Okay, that's loop 1 here, right in here. Now we're going to start on the left side of this power supply, and we're going to the right. We are losing electric potential, so you have to write minus V2. Minus V2 in our equation. Okay, we already have minus V2 here from the previous problem, right? So here you go, minus V2. What's next, right? Go. We're moving only in this loop here that contains V2, R1, and R2. Okay? Now, look what's going to happen. We are going to move from the right to the left on R1. Okay? Since we are moving against the flow of the current in R1, we're not going to lose electric potential. We're going to gain electric potential. Okay? So now we're going to have V R1, right? Like that. Plus, we're moving against the flow of electrons across a resistor. When we move up, we move against the flow of the current, not the electrons, but the current across a resistor. When we do that, we gain electric potential. And here it doesn't mind if you're moving against the current, right? Because you're still going from a higher electric potential to a lower electric potential. we still lose electric potential. It's going to be minus V1. And the final one, from, we are going in the direction of the flow of the current across a resistor. So we're going to lose electric potential, and we are going to use I2 times R2 minus I2 times R2, okay? That's our first equation. Here, I'm going to write down I1 times R2. I'm skipping a little, right? If I want to, instead of skipping, here you go, let's put it this way. VR1. Let's do it this way. And here is minus VR2, like that. Okay, that's our first equation. We're not going to solve it yet. Okay, notice that we have one equation with two unknowns, so we cannot do anything to solve this equation, to solve this problem yet, right? We are going to need at least a second equation, which is my loop number 2. Let's get loop number 2 is this one right in here. Loop number 2. And we should have loop number 3, but if I choose loop 1 and 2, we don't have to worry about loop number 3, right? So here you go. Current flowing from the negative to the positive is plus V1. Plus, I'm going to, emphasize, plus V1. Minus I1 R1 minus minus VR1, okay? You see, for loop number 2, we are going in a direction opposite in this branch here, right? Loop number 1 goes from the right to the left, but loop number 2 goes from the left to the right. So it's going to be the negative of we got for those two elements there for loop number 1, right? So, but we are going to flow through this resistor R3, right? It's going to be in the direction of the flow of the current, is going to be minus VR3. Minus VR3. So we have only 3 elements. Loop number 2, we have 1, 2, 3 elements. Loop number 1, we have 1, 2, 3, 4 elements. Okay? So that's our second equation. Let me write down in terms of the current. Here is going to be I1 R1, I3 R3. Okay? So those are my loop equations. Loop equations. We don't need to come up with another loop equation because we need just the number of loop minus 1. So here you go. Let's take a look here. Can we solve it? No, we still cannot solve, right? Unknowns. We have 2 equations and we have 3 unknowns. The unknowns are I1, I2, and I3. So we still cannot solve this set of equations. So we need one more equation. We need one more equation, the equation of the junction. Okay? And let's choose junction number 1. J1. Okay? Let's just go and this junction here. Remember, we have 2 junctions, but we need just 1 junction to solve the problem. Okay? So look what's happening here. It is as though as the current number 3 is resulting from the summation of I1 and I2, right? I3 is coming out of the junction, and I1 and I2 is going into the junction. So when we have something like that, it's going to be I3 is equal to I1 plus I2. I1 plus I2. We don't need that. And now we have three equations and three unknowns. That's the system that I mentioned to you, okay? Those problems can become very complex once you have circuits that have several loops and several junctions, okay? And the more equations we have in our circuit, it's more mathematically challenging to solve them. Here we have, three equations. We want to find I1, I2, and I3. Let's solve that. Okay, we can start by eliminating I3. Okay, let's eliminating I3. By eliminating I3, I mean I'm going to write I3 in terms of the other currents. Okay, eliminating I3. Eliminating I3. Okay, I3 is gonna fit. Oh, what did I do? I want to copy that. Good. And I want to plug it in here. And don't forget, we gotta put a parenthesis. Okay. And now look what we have. We have two equations with two unknowns, I1 and I2. Okay. And it's possible. Now it's going to be possible to solve this problem. So let's see how we are going to solve. We have to eliminate another current. In order to solve this problem, we have to eliminate now. I'm going to eliminate I2. Okay, you can choose whichever you want to eliminate. By eliminating I2, what do I mean by eliminating I2? I have to write down I2 in terms of the other values, right? So I'm passing this term to the right side to write down I2, to eliminate I2 or write I2 in terms of the other parameters. I'm going to, that's gonna go R2 right in here. Like this way. And now I solve I2 in terms of I1. Okay. I eliminated I2. Solving, next step, solving for I1. What I'm going to do, I'm going to replace I2 right in here. Okay, and we solve our problem. I will copy that right here. I2 goes right in here. Okay. The problem is almost complete. Okay, I'm going to expand everything here. This negative sign goes right in here. R3. 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 Oh, let's see. Okay. Let's see what we can do. I'm going to expand this term here. But first, let's change the sign. Okay, I'm going to, when I change the sign, this one becomes positive. This one becomes negative. and this one becomes positive, right? And then we expand everything here. We're gonna be V2 divided by R2, I1 R1 divided by R2, V1 divided by R2. And I'm going to put everything here under parentheses. And then I still have to multiply by R3. Did I make a mistake? Doesn't look like, right? Positive, negative, positive, good. Okay, R2, only R2 here. Next, do you see how much work we're having to solve this type of problem? R3, R3, and R3. Right? Copy. Like that. And now we want to solve for I1. Let's collect I1 everywhere. Here you go. Those are all the terms that we have for I1. Or all the terms that involve I1. And they are all negative. Okay, so since they are all negative, we can pass everything to the right side and become positive. Positive. One more. And put R1 in evidence. Can we put anything else in evidence? No. Just I1 in evidence. Okay, erase I1 from here because it's already outside. Okay. And then we finally solve for I1. But before we solve for I1, let's put everything under the same denominator. Right? R2 divided by R2. Like that. Let's put this one under the same denominator too. R2, R2, everything. Let's see, I'm gonna put R3 here inside. Right, and now we can put everything under the same denominator. Like that. Okay. And next step. I'm gonna put everything under the same denominator. We already have everything under the same denominator. Here we go. This one goes here. And this one goes here. Okay. Left side and right side have the same denominator, so they can cancel out. Let me unbold here. Those terms does not have to be bold-faced, only those terms that we do not know, right? Okay, and we solve for I1 now. R2 cancels out with R2, right? R2 cancels out with R2. And this R1, this combination of R1, R2, and R3, right? Something like that. V1 plus V2. Okay, so that's well, it's not the complete solution of the problem because we still have to walk back now, right? For the other ones. I1, well, we want to find I2. Where is I2? That's I2. So for I2. So for I2, right? We place I1 right in here. It's going to be a big, right? A big thing, right? Whether we can simplify it or not, we do not know, right? So for I3. So for I3, the I3 is right in here. I1 plus I2. Now we solve I2. Right, with I2 here, right? And I'm not going to do that, okay? But you got the idea, right? All you have to do now is just to do the mathematical derivation. Okay, that's 1125. And did you get an idea how we solve those problems? Let's see how many pages here we got. One, yeah, we got kind of, well, the drawings occupy lots of space, right? But the mathematical relations occupy what? 2 pages in the derivation. 1, 2 pages. Maybe 3 pages if we consider what was written as well along the way, okay? So that's the type of problem that we see. That's the type of problem that this technique solves. One of the types of problem that this technique solves. Example, go. And let's move forward now. Let's get. So let's situate ourselves. Okay, here we go. We did electromotive force and current, Ohm's law, resistance and resistivity. We still didn't do electric power. We are going to do alternating current later on. We did this one. We did this one. Circuit. We did this one. We will not do 20.9. And here we go. We have this. We have done this one as well. Conservation of energy and charge. Okay, that's what Kirchhoff rules is all about. When we go through the loops, we are using the statement of conservation of energy. Okay, so right in here, when we go through each of those loops, basically we are using the statement of conservation of energy, since electric potential is a potential energy, is related to the potential energy. And the case here for the junction, we are relating the current with each other. What are we doing? We are using the statement of conservation of electric charge. That's what it means. Okay? Whatever arrives here at this point must be equal to whatever exits the same point. That's what we are doing. The number of charges, right? The total amount of charge is conserved. Here, 20, we're going to do that in the lab. And let's do this one right in here. Capacitors in series and parallel. And I'm going to unbold it right now. Okay, so I want to remind you what we did before, right? Resistors that use Ohm's law have the following relationship with respect to the electric potential and the electric charge. The resistance is directly proportional to the V. However, for the capacitance, we still involve the same parameters, quite of the same parameters, right? But it's going to be an inverse relation. The Q that's here is the same as this Q right in here. This V that's in here is the same as the V that's in here. Okay? And notice that if we define what I call an incapacitance, which is the inverse of the capacitance, we notice that, you know, the V is going to be at the top, just like we have the V at the top here for the resistor. And the Q is going to be at the bottom, just like we have the Q at the bottom here, okay? This definition doesn't follow the same property of direct proportion, just because of the definition, just because of its definition. If you were to define something else called capacitance, we would end up having the same proportionality with those parameters, okay? But, you know, but because we define the capacitance in this way, contrary to the way we define the resistance, okay? We can now go back, you know, we can now, what happens? We can now start asking, all right, what happens when we connect capacitors in series and parallel? Okay, the fact that we have those two relations here already give us a hint how capacitors in series, what's going to be the equivalent capacitance of capacitors connected in series, and similarly for capacitors connected in parallel. And I want to remind you of the relation for resistors in series and parallel, okay? Let's remind you. I drew that table for you, remember? Okay, here you go, for resistors. We can do a similar table for capacitors. Okay. Resistors connected in series, the equivalent resistance is going to be the summation of the resistors of each separate resistors. Resistors connected in parallel, the inverse of the equivalent resistance is going to be equal to the summation of the inverse of each resistance. The summation of the inverse of the inverse of each resistor. Okay. And then what happens to capacitor? Capacitor, something quite of similar happens. It's not exactly the same. But I'm going to give you the final solution, right? And then I will walk you through the derivation. It's possible to do that. Okay, so the final solution is this one, like right in here. Like in comparison, right? Resistors in series is the summation of all resistors. Resistors in parallel, the inverse of the equivalent resistance is going to be equal to the summation of the inverse of the resistors, the inverse of the resistance. Okay, Now, because we have this relation here, because the capacitance is inversely proportional to V and the resistance is directly proportional to V, what's going to happen to the equivalent capacitance? The equivalent capacitance is going to invert, okay? Here, see that? For capacitors in series, the equivalent capacitance, the equation for the equivalent capacitance is going to be similar to the equation for the equivalent resistance, okay? Just because of that proportionality that was inverted. It's an interest. And when you connect capacitors in parallel, the equivalent capacitance is going to be given by the same formula of that, the equivalent resistance in series, okay? Just because of that proportionality relation that I showed to you, okay? So it's flipped, right? It's flipped. And we can prove that. It's possible to prove that mathematically. And the way we do it is by conservation of charge, of electric charge, and conservation of energy, okay? And here I have another table for voltage, okay? Capacitors that are, the resistors that are in series, the V, the net V is going to be the summation of all V's. For resistors and capacitors that are in parallel, we do have conservation of energy, right? And current and charge, conservation of current and charge. Whenever we have resistors in series and capacitors in series, okay, the current is going to be the same through each resistor, and the charge is going to be the same through each capacitor. So that's the starting point here to find out what is, to get this result that you see right in here, okay? That's the starting point. And whenever you have resistors in parallel, the net current is going to be the summation of the current through each resistor. Similarly, whenever you have capacitors in parallel, the net charge is going to be the summation of the charges in each capacitor. And I can illustrate that. Let me give an illustration here, 1136. Connecting capacitors in series and parallel, okay? So here you go, capacitor in parallel here, capacitors in series here. Okay, so we have this simple circuit, no resistors whatsoever, just capacitors, two capacitors in series. And what's going to happen here? When we close the circuit, the electric potential across this capacitor plus the electric potential across this capacitor must be equal to V, conservation of potential energy, okay? But you also have to think in terms of the charge. What's going to happen when we close the circuit, right? We insert those capacitors that are initially uncharged. The circuit is open. There is no current flowing through the circuit. We close the circuit. And now the positive charges are going to flow towards this plate of the capacitor. And the negative charges are going to flow towards the plate of this other capacitor. Can you picture that? The charges can move in the wire, right? And here you go. That's what we have. And something else is going to happen too, to the other side, to the other plate of the capacitor. Those negative charges are going to attract the positive charges that are here and repel the negative charges that is in this region. And then what's going to happen? You know? They're going to move, depending on the charge, they're going to move towards or away. The positive charges that are in this capacitor are going to be attracted. The positive charges that is in this other capacitor are going to stay here. And these negative charges are going to be repelled by this negative charge. Okay? That's how you should look at it. And then what you're going to end up having, we're going to end up having something like that. two capacitors that are charged. Let's say that are fully charged. That's a nice step-by-step explanation of what happens. Okay, and because of conservation of charges, the charge in this capacitor must be equal to the charge in this capacitor. Do you see I put two charges here, two positive charges here? I did that on purpose. Okay. And I did that on purpose. In addition to that, let's do that here. I'm going to spell that out for you. Okay. Consider, that's the final solution, right? But we start from here. The final solution is this one here. But I'm going to put this one at the top. Like that. Like that. What you have here and here is exactly what you have here. Okay? What is new? The capacitor column is new. Okay? So connecting, this is the final answer. What you see here is the final answer, okay? For this one, connecting two capacitors in series. Two capacitors in series to a battery. Connecting two capacitors in series to a battery. Right in here. Capacitors are originally discharged. Okay. Something like that. Originally discharged. Okay. Once you connect the two capacitors, current start to flow in the circuit. The current is going to flow in this direction. Okay. Initially, well, we're doing step by step here. This left side of the capacitor is going to fill up with positive charge because it's facing the positive side of the battery. And this other side of the capacitor is going to become negatively charged because it's facing the negative charges are flowing in this circuit. Okay? And copy and paste here. So I'm going to, when we close the circuit, okay, when you close the above circuit, positive charges will flow towards the leftmost plate of the left capacitor. Conversely, negative charges will flow towards the rightmost plate of the right capacitor. Okay. Next, the right, the leftmost, let's see, the leftmost plate of the left capacitor will attract the negative charges, will attract the negative charges in the other, in its corresponding plate. Likewise, the rightmost plate of the right capacitor will attract the positive charges in its corresponding plate. We attract the negative charges, right? And I'm going to illustrate that as well. I'm not going to illustrate everything because otherwise we're going to get too much. Here you go. That's how we tell the story of how capacitors behave. Remember, capacitors are not like batteries, right? Batteries can keep their charge separate on their own. Capacitors not. No, they don't work like that. They can lose their charge as time goes by. Okay, capacitors do not have that chemical power plant to separate negative from positive charges. It has only a dielectric that prevents those two charges to interact. And what's making the capacitor become charged? Well, it's the fact that it's connected to a battery. A capacitor doesn't charge on its own, okay? A capacitor can only become uncharged on its own, but it doesn't get charged on its own. It needs a battery to become charged on its own. And okay, and that's the picture. Okay, step by step. Okay, by conservation of energy, okay, we must have just like we had with the resistor, we must have let's see, V1. V1 is the electric potential difference in the capacitor 1, and V2 is the electric potential difference in the capacitor 2. Is going to be equal to V. Okay. And by conservation of electric charge, we must have Q1 equal to Q2. Okay. Q1 equal to Q2. And let's see if I have written that here for you. Oh yeah, here you go. I have this one here for you. See that? When we separate the charge, this capacitor becomes charged with Q1 and this capacitor becomes charged with Q2. Since the system was originally neutral, in order to have conservation of charge, the amount of charge here, Q2, must be equal to Q1. They must cancel, okay? By the same token, this positive here, the number of positive charges must be the same number of negative charges here to yield a net zero charge. That's how we should interpret that. I'm going to, this is an important drawing. Okay. like that. Like that. Okay. If you sum this charge with this charge, you must have zero net charge because we started with a neutral capacitor originally. Okay, and now I can do the derivation that I promised to do for you. Okay, and how does it go? How does it go? Okay, we're using. Let's start with the conservation of electric potential. Okay, so here you go. I will be able to, to prove to you that the capacitors in series will have an equivalent capacitance equal to that. Okay, and capacitors in series. In series. Here you go. V equal to V1 plus V2, and Q1 is equal to Q2, which is equal to Q. Okay. Recall the equation for capacitance. Okay, recall the equation for capacitance. Let's get that. We're going to need that right in here. Okay. That's the equation for capacitance here. Okay. Since those capacitors are in parallel to each other, okay, we are going to rewrite this equation here in terms of the equivalent capacitance. Okay, equivalent capacitance. Since we have two capacitors in series, the V that you see here is going to be V1 plus V2. Okay, V1 plus V2. And now I'm going to invert both sides of the equation. Okay, I'm going to invert both sides of the equation. Of this equation. Here goes. It's going to be, it's a mathematical trick that we end up discovering after thinking very hard about it. Okay. This is a mathematical trick that we discovered a long time ago. It's a nice, okay. Two capacitors in series. Okay. And then I'm going to, what I'm going to do? I'm going to invert that, the right side of this equation. Okay, so here you go. And now what else I'm going to do? I am going to break down this equation into two. It's a nice little mathematical trick, right? And then what else? What else is going to happen? Look what the nice thing that's going to happen. Refer to this equation for the capacitor, right? By the same token that C is equal to QV, by the same token that C equivalent is equal to Q over V, we can also here write C1 equal to Q divided by V1. Strictly speaking, you should be writing Q1 here, right? But because we are dealing with two capacitors in series, the Q1 is going to be equal to Q. And the same thing can be said about the C2. Okay? Q equal to V2. And now we are going to use those two relations right in here. Okay, right in here, right? Take a look. Take a look. C1 is Q over V1. Here is V1 over Q, right? So this first term must be the inverse of capacitance 1. And this second term must be the inverse of capacitance of the capacitor 2. Okay? So I have proven this relation here for you. And we can do the same for capacitors in parallel. And we will end up getting that. Okay? Can you remember that? Okay? If resistors in series, the equivalent resistance is going to be the sum of the resistors, and resistors in parallel, the inverse of the equivalent resistance is going to be equal to the summation of the inverse of each resistor separately. When you connect capacitors in series and parallel, the relation is going to be the opposite. And the relation is the opposite because of that way that we define capacitance and resistance, right? One is directly proportional to V, the other is inversely proportional to V. Directly proportional to V, inversely proportional to V. That's why we get that flip in the equivalent capacitance in series and parallel. Okay, so that's the explanation for that. And that the same thing can be repeated for n capacitors in parallel, n capacitors in series, and so on. Okay. Any questions? 11:55. I think that's a good time to go to our break. And I'm going to write down here, break 11:55 a.m. to 12:10 p.m. Any questions before you go for a break? Okay, I see you in 15 minutes. Okay. Okay, so we did capacitors in series and parallel. I think for now, let's see. I'm thinking about skipping this one. Okay, maybe we have time to do that, to go back to that. This one we will. Oh, I gotta do this electric power. Okay, so let's see. Alternating circuit we're going to see later on, but we gotta do electric power now. For now, let's skip RC circuits. Okay, and let me copy and paste. Well, then we go. Let's look at the electric power. Okay, so we go. The idea of electric power is the same, parallels that idea of mechanical power. It's no different, okay, than what we have seen before, okay? Power is the amount of energy per unit of time. This same concept is also applied to electric and electronic circuits, okay? So why we need that? Okay, well, if you're building an electric circuit or an electronic circuit, you have to know how much power is going to spend so you can design your source to provide that amount, at least that amount of power. If you have for instance, a power source that can provide 3 watts, right, of energy, but then you have an element that can consume 3 watts, that's okay. The battery will be able to provide that energy per unit of time to that element, right? However, if you get an element that's gonna spend not 3 watts, but it's going to spend 100 watts, the power source of 3 watts is not going to be able to keep up with how much power the other element is sucking out, okay? It's just the case of I'm going to give you an example, okay? I'm going to give you an example. I bought those no brakes that I mentioned to you at the beginning of the course, right? And so that no brake has a limit, has a given amount of power, okay? If I connected that power, their no brake to too many equipments, to lots of equipments, what's going to happen? That no brake is going to exhaust its power almost instantaneously, and that happened to me. Okay, I got a no brake. I didn't do I didn't do my homework. I didn't do how much each device was. I didn't found out. I didn't sum up the power consumption of each device. When I connect the devices to the no brake just run out of power just like that quickly. And then I cut down the amount of the devices connected to my no brake, and it lasted longer, okay? So that's why we introduced this idea of electric power. Okay, batteries and capacitors, they have a given amount of energy stored on them. So batteries and capacitors can be thought as though they are sources of energy. However, a resistor, no, a resistor consumes energy. Okay, that's why we get that electric potential negative when we go through a resistor, in the direction of the current. And so here you go. So we need something like that to estimate how long your source is going to last. Your battery, your source is going to last. What battery you will need to power the circuit for a given amount of time. And I used to do this type of things. I do that all the time, okay? If I want to power my circuit just with a battery, I have to know, instead of connecting to the electricity, right? Batteries, they run out of power eventually, right? But some time ago, I was powering a circuit of mine, and I knew that with the battery I was using, that battery is going to last like 8 hours feeding that system. Okay. But now the question is, how do you calculate the powers consumed by a circuit? There's a nice, straightforward way to find that out. It's not difficult, okay? All you have to do is to start with the equation for the power. Is the amount of potential energy, the amount of energy per unit of time. Okay? But recall the definition of electric potential. What is the definition of electric potential? Right? Electric potential, delta V, is going to be delta U divided by Q. Okay? I can even include delta Q here as well, if I want. And this delta U will be here written, can be here written as delta V and delta Q. Oops. Delta V and delta Q. And now I can replace delta U in this equation. Right? Right in here. There you go. And then what's going to happen? we note that now we have delta Q over delta T, right? And delta Q over delta T is what? Is the current in the circuit. It's a rather straightforward way of deriving the power, okay? We're going to simplify this equation just by calling delta V equal to V, okay? Simplifying, or just simplifying this equation, VI, even better, VI. VI. Like that, VI. But there are other ways of writing. Here you go. There are other ways of writing this equation. Okay, recall that if we use Ohm's law, V is equal to Ri, right? If V is equal to Ri, we can also written this equation as Ri squared. Another way of writing the power. And there is one more way of writing the power, just R equal to V over I, right? Let's see. No. It's the other. It's I equal to V over R. That's the one we have to use. Okay. It becomes V over R square V square okay, and here you go. Just another relation for the power is this R cancel out with the other R. So we have three different equations that may be used depending on the device that we are talking about. Okay, they all produce the same result if whichever you use. Here you go, VI RI square or V square over R. Okay. This one is more appropriate to find out the power expand by a resistor. Here, this one here is more appropriate to find out the power provided by a battery. Okay, and so on. Here too, we can use this one to find out the power it's spent by a battery. Okay, and now we can come up with some exercises. Okay. Exercise. Flashlight with a current of 0.4 amps, powered by a 3-volt battery. Find the power delivered to the bulb. Okay. The energy dissipated by the bulb in 5.5 minutes. Two different items, right? Solution. Find the power delivered, right? To the bulb. Delivered to the bulb means, what does it mean? Power provided by the battery. Okay? That's what it means. So, item A. Item A. VI. Okay, the battery is 3 volts. So you go ahead and write down 3 volts here. And the current is 0.4 amps. Okay, so that's simple enough, right? 1.2 volt amp. Okay, volt amp. And since we're talking about power, we should get a unit of watts, right? Let's see if you get watts. Okay, let's see if you really get watts. Volts is what? Joules per coulomb, right? And amps is what? Is coulomb per second. Let's see if we get exactly what we are supposed to get. Coulomb cancel out with coulomb, right? Coulomb here cancel out with coulomb. We are left with joules. And then we are left with joules per second. And joules per second is what? Unit of power. That's the watt. So one more student coming in. Here we go. 1.2 watts. Okay. Find the energy dissipated by the bulb in 5.5 minutes. Okay, item B. Item B. The energy that's being provided to the bulb is the power that's provided to the bulb is 1.2 watts. Okay. And which is joules per second, right? Let's rewrite that. 1.2 joules per second. And delta U must be equal to power times delta T. Delta T. We're talking about 5.5 minutes. So power is 1.2 watts. Delta T is 5.5 minutes. Yeah, I'm going to emphasize that this watt is joules per second. Consequently, we must change this unit to seconds. 1 minute has 60 seconds. Like that. Okay. Then do the math, right? 1.2 times 5.5 times 60. What? 5 minutes is 300 seconds, 330 seconds, five and a half. 300. What we end up getting, is just 396 joules. Right? That's the amount of energy that the resistor, that the bulb consumes. 396, sorry. 96 joules. 1230. Yeah, so let's follow. We have 20 more minutes to go. Okay. for now, we're going to skip that. Okay, and later on, we're going to look into that. Okay, so what I want to do now is to start chapter 21. Okay. This one here, we're going to go back when we start looking at AC circuits. That there'll be a chapter on AC circuits further down the line. Okay. And will be more appropriate if we go back to this one at that time. Okay. What's chapter 21? And let's take a look at our book. Chapter 21, right in here. Magnetic fields. Okay, well, here you go. Magnetic force. Magnetic force and magnetic field. First is magnetic force, right? We represent the magnetic word by the letter B. Magnetic force and fields. B stands for the magnet, the letter magnet, the word magnetic. This has been known since antiquity. Okay, so the Greeks knew about that. Ancient Greeks, they knew about static electricity, and they also knew about magnetic force, the electric force and the magnetic force. Okay, together with electric force, along with electric forces, electric force, magnetic force was also known by the ancient Greeks. So how did they knew about that, right? How did they knew about electric force? They knew about electric force because of static electricity. In very dry weather, people would become electrically charged, right? And then once you're electrically charged, you have that funny feeling, and people start thinking about why something like that is happening, right? That's straightforward. But what about magnetic force? How did they knew about magnetic force, right? Well, they knew about magnetic force because there are naturally magnetized minerals. There are naturally magnetized minerals. They're called lodestone. And those minerals, they exert force in iron, a force in iron filings. So they start seeing that and they start thinking why those stones are tracked by iron filings, right? And then we start thinking about that and start making hypotheses over that. Later on, the Chinese, not the Chinese, maybe the Mongolian, we say that it was the Chinese, right? If you go to who invented the compass, they say it was the Chinese who invented the compass. But I suspect it was the Mongolian, the compass. Who invented the compass? I'll say, yeah, it was in China. The Han Dynasty, 2nd century BC. Okay, it was the 2nd century BC. The Mongolians came afterwards. Genghis Khan, right, and Kublai Khan. You have heard of them? And those guys are around the 1200. 1,000 years after. So the Chinese discovered that magnetized needles would point in the north-south direction. And it was something that Marco Polo discovered right when he was visiting that region. So pieces of lodestone would point in the north-south direction. this device started to be used as a rudimentary compass. It was initially used for divination purposes and later on for navigation purposes. Okay, that's how people found out about the magnetic field, the magnetic force first, right? The idea of magnetic field comes afterwards. So there's some interesting similarities and difference between magnetic and electric forces. Okay, magnetic, electric versus magnetic forces. Let's go. Let's see if I can come up with a table. Similarities. Two poles, right? Two poles, attractive, and repulsive forces. Those are similarities. But differences. Magnetic poles cannot be separated. Okay, that's a very important difference. Magnetic poles cannot be separated. Electric poles, which are the electric charges, whereas the electric poles or charges, they can be separated from each other. That's the difference. One of the difference. There's one more difference. The source of electric fields, electric force, is like field, is the electric charge. By the way, what you see right in here is one of the laws of physics, okay? One of the laws of physics. Magnetic poles cannot be separated. Source of electric field is the electric charge versus source of magnetic field is not the electric charge, is the electric current. Okay? Do you get that? You know? So an electric charge at rest generates an electric field, but does not generate a magnetic field. A magnetic field, a B field. However, if you put this charge to move, a moving electric charge produces both an electric field and a magnetic field. That's another difference. The source of electric field is electric charge. The source of magnetic field is electric charge that is moving. If you want to create a magnetic field, a magnetic force, you've got to put your electric charge to move. You got to make your electric charge move. Okay? I'm gonna put in a better way here. Okay, like differences. Isolated electric charges exist versus isolated magnetic charges do not exist. Two electric charges, two magnetic charges. Positive electric charge and positive north magnetic charge. Negative electric charge and negative magnetic charge. A positive electric charge attracts a negative electric charge. Those are similarities. Okay, I didn't put that at the top. Similarly, a positive magnetic charge attracts a negative magnetic charge and vice versa. Like electric charges repel one another, similarly, like magnetic charges repel each other as well. Repel each other as well. Oh, okay, I gotta put it here. Another difference, right? Charges at rest generate an electric field versus moving charges generate a B field. That's important differences between them. 1239 right now. Do you get that? Okay. This is a law of physics. Law of physics. This is another law of physics. Okay. Okay, this is another law of physics. Positive law of physics. The magnetic law. That's the law of attraction. Keep that in mind. This 1240, do you have? Well, we go until 1250. Okay. Let's extend a little bit more. Okay. Okay. And what else? Another important. Let me get some drawings here, some illustrations. Try to make everything come alive. Let's see if I have any more illustrations here. Okay. Magnetic field. Okay, so here you go. Here's an illustration of a magnet, of a source of magnetic field, a source of magnetic force. Okay, is what we call the magnetic dipole. By the same token that we have an electric dipole, there's a combination of positive and negative electric charges. We also have a combination of north and negative, of positive and negative electric poles. The north pole is said to be the positive pole. The south pole is said to be the negative pole. Okay? That. Now, what else? North and south poles cannot be separated. Positive and negative poles, they cannot be separated. And that's one of the laws of physics. Okay? You cannot, if you break the magnet, you are not going to keep a north pole separated from the south pole. No. If you break a magnet in half, the south pole is going to form in the upper pole, and the north pole is going to form in the lower pole. And this is one of the laws of physics and a difference between electric and magnetic source. The magnetic field, comes out of the north, of the positive, and the north pole is a source of magnetic field. The south pole is a sink of magnetic fields. And if you put a magnetic compass nearby this magnetic pole, it's going to point tangent to the magnetic field lines. Okay, so let's write it down too. Here you go. Okay. If a magnet has two poles, the north or positive pole and the south or the negative pole. Okay. If you break a magnet in half, okay, a magnet has two poles, north. Okay, because it has two poles, it is referred as a magnet dipole. Okay? If you break a magnet in half, another smaller magnetic dipole is formed. You will never be able to separate one magnet from the other. Okay? That's what is spelled out right here. What else do we know? We also know that the Earth behaves like a giant magnet. Okay? The Earth has its axis of rotation. Its axis of rotation is located at the north and south pole. It intersects the Earth's surface at the north and south pole. Okay? That's what we call the north and south geographic pole. Here, north geographic pole, south geographic pole. But we also know, like I said, that the Earth behaves like a magnet as well. Okay, a magnet, it is just like that. And I'm gonna make it simpler first, and then I'm gonna evolve towards something more complicated. Okay, here you go. Here's the giant magnet that the Earth is, and it just like the axis of the Earth intersects the Earth's surface at two different points. The axis of this giant magnet that the Earth is also intersect the Earth at two different points as well. And those 2 points are very close to the north and the south geographical pole. Okay. Another piece of information that you must remember: you go the Earth. It was hypothesized by the Chinese and the Mongols that Earth is a huge magnet. What else did they discover? They also discovered that the magnetized needle of a compass points towards a direction that is very close to the north-south direction. Okay? Very important piece of information here. And what else you have to know? Here you go. Points very close. Why does it point very close? That's because the poles, the north and south magnetic poles, is very close to the north and south geographic pole. Okay, very close to the north and south geographic pole. And there is one more important thing about the Earth's magnetic field. Although those two poles are very close to the north and south geographic pole, they are inverted. We are at a moment in the Earth history that the north magnetic pole is nearby the south geographic pole, and the south magnetic pole is nearby the north geographic pole. Okay? Every now and then, every 100,000 years, this polarity of the magnets flips back and forth. Scientists have found that out. They have evidence for that. Okay? So let's write it down too. Students coming. They also discovered the magnetized needle. Okay, that's because today, that is because the Earth's magnetic poles are very close to the Earth's geographic poles. And the difference between the magnetic pole and the geographic pole, right? The geographic pole are the points where the Earth of rotation of the Earth intersects the surface of the Earth. Okay. There's a very because the magnetic and geographic poles are not collocated, right? Collocated. It means that your compass points to a direction that is slightly off the actual north-south direction. Depending where you are on the Earth, this difference can be of 12 degrees. Depending, it can be even more than that, okay? Depending on what position you are, right? This difference can be even more than that, can be even 180 degrees, okay? If you're nearby the poles, that difference can be 180 degrees. Okay, so it's 12:50 right now. Those are the pieces of information that you gotta know, and we will continue on that next time. Do you have any questions? Don't forget that we have an exam the day after tomorrow. Okay, you can log into Canvas, and you should, for the exam, you must be logged into Canvas and this Zoom address. Okay, make sure you are logged in there. I'll need to see you, okay, to monitor you. So I see you the day after tomorrow, right? So see you then. Thank you for being here, by the way.
Professor, I have a question about the exam. Are we gonna start right at 9:50? Or are we gonna start like earlier?
No, 9:40, right? Did I put 9:40?
Oh, 9:40, sorry.
Yeah, 9.
So right at 9:40.
Yeah. Let me see.
Okay.
Let me check I didn't make any mistake at the syllabus, right? Did I put the right time? Let's see here. Syllabus. Yeah, 9:40. 9:40 to 11:40. Okay.
Okay, thank you, Professor.
Okay, thank you.
Thank you, Professor.
Yeah.